us, Paul? Can you hear us?
Oh.
No. We not have speakers working.
Uh,
They didn't move their mouths, so they didn't hear it.
Beth, can you hear us?
Oh.
Beth can hear us. She gave us a thumbs up.
Okay,
Okay, without further ado, I give you.
Yeah, I can hear you fine.
Sorry, number 15.
I can hear you.
all right, so many people go to math journals to get their mathematics. Many people aspire to get into famous math journals. Some people like to get onto the cover of Science magazine or Nature. But some people go to their local, I don't know what Esquire is really, a men's lifestyle magazine or fashion magazine. And if last year you happened to be going there and perusing it looking for important mathematics, you would have come across this article, which says that mathematicians discovered something mind-blowing about the number 50. So what I want to talk about today is helped start the problem. I didn't solve it, but I did help start the problem. So I managed to make it into Esquire magazine, though I'm not mentioned. And so my goal is to tell you about the problem, which I will be able to find, and then talk to you about why it is actually some reason for it to be published and be spoken about. Whether it's mind-blowing about the number 15, I'll leave it to that. So what I want to do is pause the screen and start chalking. So let me get to what the problem is that I want to talk about. So I'm going to have a grid. Think of this as the infinite grid. 5 by 5. I'll get there in stages. So I'll do a few warm-up problems first, then we'll get to the one that made it. So we have the grid, and in all cases, we're going to fill with the integers from 1 up to some value, say b, and we want b to be as small as possible. So the answer to the first question, of course, is 1, because you just put 1 in every cell. Okay, probably go a bit deeper in that. So the first question one could consider is, if you want no two adjacent cells or squares to have the same number. And if you've played this game before, you sort of by adjacent, you mean the corner, touching at the corners or not, and the answer is no. What I want is that if this value, if there's a 1 over here, I can't have a 1 there, or there. And the answer to this question is, of course, 2, because you can put a 2 in every space, and then you can put a 1 in, and so on. The obvious checkerboard idea. Right. So let me slightly rephrase that. This is what I like about being able to give a talk and not a class lecture, because I can erase thing. I don't know if people do have people taking notes. Okay, so we want. Let me phrase this as follows. Any two copies of I are more than one apart. Let me rephrase this in terms of thing. So these are one apart, they have to be different. These are two apart, because we're not going diagonally, and they can be the same. All right. So a second problem, suppose I change the distance apart slightly. So instead of being one apart, let's have two apart. Again, you care about that whenever you pick it, two copies of the same number, they have to be more than two apart. And I know I could write these as inequality, as greater than or equal to, but greater than is the one that makes it easiest to say. So what does that mean? That means back over here, when you have one, you can't have any neighbor of it having the same value one. And you can't have this thing over here because that's distance two. And again, you probably realize I should have mentioned there's lots of ways you can measure distance. You may have noticed that in as a mathematician. And what I mean is what's sometimes called the Manhattan thing or the L1 norm thing that you consider how many steps do you have to go. So you there's four things at distance one, at distance two, I think there's 8. So if you put a 1 there, you can't put a 1 in any of those squares. Okay, well, I mean, we had this problem. We could try it. You could put a 1 there, and a 2 there, and a 3 there. And then a 1 there and a 2 there and a 3 there, and you could do that going on to infinity. But if you try that, you realize you run into issues down here that you can't use 1, 2, or 3 for this one, if once you have that and so on. So it turns out the answer to this one is 5. And the reasoning for that, well, first of all, there's two things that you have to do. Is first of all, I have to convince you that in fact 5 is possible. And secondly, I have to convince you that 4 is not. So let's see if I got this right. Preventative practice. Okay. So let's consider the ones arranged in that way, like knight's moves or something like that. Then the claim is locally we find there's distance 2, distance 3 there, distance 3, distance 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And if you take this picture and you copy it on that side and that side and that side, you can make this do the infinite plane with this thing. And the ones will all be valid places of putting the ones. Agreed? Thanks. Now, where does the next? Well, then you just take the entire picture and shift it one to the right, and you put all your 2's over there. And then you do the same with the 3's, the same with the 4's, and the same with the 5's. And remember, there will be either one sitting over there because this picture is repeating. So we end up having this very nice picture of we're using the numbers 1, 2, 3, 4, and 5. All right. Now, so these two, but this is mathematics, so we need two parts. One is a demonstration that 5 is possible, and the way all the demonstrations in this situation are examples. Here's the picture. And then the perhaps more interesting question, and eventually becomes the very hard question, is how to show that this is best possible, that you can't do it with 4. So over here, for this particular problem, there's lots of ways to do it, and I'm sure you could try it. But one way to proceed is to say, if I take a 1 and I consider the force held right next to it, distance 1, each of this thing cannot be distance 1 from any other one. Because otherwise, if there was a 1 over there, then the ones would be too close. So you can sort of take this, think of this as being part of one's kingdom, or whatever phraseology you want to think. So one's territory is this like plus situation. And so what that means is that if you think about this plane divides into this territory, and only 1/5 of the cells can be occupied by one. Because every one has this area around it. And in fact, that's how you find the pattern. Once you realize that, then it's basically it's taking this plus sign and packing it onto the plane such that every cell is covered. So it's sort of a density argument. You can't use the one more than 1/5 of the time. So the actual question that was asked is this following, so right there to define it. So the problem that was defined, it says the following: we're going to treat the numbers differently. Up until now, we say all the numbers are the same, and the condition for 1 is the same as the condition for 2. But here we're going to mix it up a little bit. We're going to say the condition for 1 is that two copies of 1 must be more than 1 apart. So that was the original thing. You can use lots of 1s, right? We can do half the squares can be 1s. The conditions for 2 is that every instance of 2 are more than 2 apart. And we've seen that we can do roughly 1/5 of the plane we can do with 2 if we're lucky. And then 3's have to be more than 3 apart. So whatever that is, and so on. So just to make sure we are on the same way, we wanted to play the game not on the grid, but just on the two-dimensional plane, on the one-dimensional plane, also known as a line. You can put a 1 there, and a 1 there, and a 1 there, and a 1 there, and a 1 there, going on to a thing because they do. You can put a 2 there, but you can't put a 2 there, but you can put a 2 there because that's far enough apart. And you can put a 3 there and a 3 there because that's far enough apart. So you can have every alternate one is a 1, and then every fourth is a 2, and every fourth is a 3. And so this was the problem. You could do that with 3. So a little bit of background. As most of you know, in our discussion, I'm a graph theorist. So what happened was I got to Clemson, and this is in 2002. I just arrived at Clemson, and there was a group of us with 3 people at Clemson and 2 people over at Furman, and we were looking around for some problem to work on. And we like coloring problems, and there's lots of coloring problems in graphs, but they all treat all the colors the same. And we said, okay, somebody had talked about thinking of this idea as being something related to like a broadcasting problem where different radio towers have different powers and things like that. These things really do show up in operations research literature. And we said, okay, maybe, how about this? And this was more like a proof of concept saying, here's a problem, we treat the colors differently, maybe you get something interesting out of it. Because this is the truth of the fact in mathematics. A lot of things are tried and then completely forgotten. The ones that help, or the ones that, for some reason, people like them or they're useful or they're something. So that's the one we tried. And so the other thing, obviously, is we're a graph theorist. So we've got lots of graphs that we care about, and certainly the grid is can be thought of as a graph if you have a vertex at each thing and you join them up. But it's only one of many, many graphs. And we had lots of problems that we couldn't solve about this thing. And most important, so we're doing this, we find various results about various graphs. One of the things that we think, okay, what about the grid? And then the first question for the grid was, is there in fact a B that does the job? And it wasn't obvious whether there was actually a finite value of B that would allow you to do this. Well, you can try, you at least try the lower bound idea. So you can know that the ones can only do a half of the thing, the twos can only do a fifth of them, the threes can only do whatever the formula is, and you can sum up those numbers. And if those numbers sum up to something less than one, then you're going to need infinitely many numbers. But if you sum those up, they go like sort of inverse quadratic, and it turns out they sum to something bigger than one. So that told us nothing. So what else can we do? So I like computers. So I come along and say, okay, well, maybe a computer will find us something for this. So at least, I don't mind duplicating things, but at least we point out something. So for example, now you want to use a computer to try and find this pattern. The pattern is infinite. What I'm going to do is I'm going to try and play the same game I did on question 2. I find a small piece of the plane, I find a pattern of there, then I can tile the rest of the plane. That's what I'm trying to find. Lots of possibilities. So at least that first pass, I remember looking this up and knowing this and saying, well, let me just assume the ones behave like this. I don't know if this is the best that you can do with the ones, but they certainly good. If you do the twos, you can do a 2 there, a 2 there, you can't do a 2 there. But you can do a 3 there and a 3 there, and you sort of get a thing where the 1s, 2s, and 3s leave holes like a grid of holes which are distance 2 apart on this thing. And then you can try and fill that, and then I thought, well, maybe there's a reasonably obvious way to try doing the next numbers 4, 5, and 6, and 7. So maybe that will work. I haul out my computer, see if it will. I don't even remember, sort of some sort of random AI type thing where you just randomly try something, and then if it's close, then you tweak it or you human look it. And eventually I showed, well, I don't know how long. Anyway, I managed to show that it was at most 23. So in particular, it was finite. That it was possible to solve this problem, use only the numbers from 1 up to 23. And in the original paper that's published, we have the following thing. So what this does is take the picture here where you ignore the 1s, 2s, and 3s. So we're now filling in the remaining quarter of the grid. And as you can obviously see, this works. Okay. Computer claimed it worked. I presumed it did. I was very happy that it had been finite, because it was starting to get annoying that we couldn't even prove that it was finite. And we did this, and it was good. And somewhere we left in the end of the paper, we called it broadcast chromatic number, which the community decided was the wrong name, and immediately renamed it to packing chromatic number, and asked, okay, so this is what's the biggest grid that, I don't know, something like this. That's what we left it as an open question. We also left quite a few open questions and other stuff, and it sort of happened like that. All right. Pause that for a moment. So what happens? This is published in a completely obscure journal. We work on various other, I work with another student on related questions about using different colors. And I sort of know how to see out of the corner of my mind, because my paper's getting cited, that people are working on the grid problem. I don't even know, I don't know the details, but I know that there's some papers, and every now and again so-and-so has improved the thing. So we were able to show that B was at least 9, and the way we did that was we took a grid, a blank grid again, of some finite piece of the thing, and showed that if you try to use just the numbers 1 through 9 for even just this piece, you would run into a problem. And the only way we knew how to do it was a brute force computer search, meaning trial possibilities for that, trial possibilities for that, which doesn't conflict with that, trial possibilities for that, it doesn't conflict with that, and so on, and just walk your way through. Okay, this is 20 years ago. If I did this on my computer now, I would run a bit faster. But anyway, so we got 9 out of the corner of my eye. I know people are doing, and some people, I know this number is going, is thing, and this number we already knew some person had not used a computer and immediately got it down to 22, and they just kept on going. And I sort of, oh, well, okay, whatever. And then last year, around about this time, actually, maybe just a little bit earlier, I get an email from a student saying they've solved my problem. And the answer is, mind-blowingly, 50. Okay. I said thanks, or sort of type of thing, and trying not to be too things, saying I still don't think it's a particularly important problem, and it's just one case of many problems we couldn't solve, but hey, thanks. But it turns out it's a very interesting way that they solved it. So what they did was, what had the predecessor, before they got into working, actually, it was like this. So what does that mean? That means there was a coloring known that uses 15. Somebody had done it. I don't know whether it was something else, but that was known. And somebody had proven that you couldn't do it with 12. And their job was to do this, and they got it up to 14 reasonably straightforwardly. And then the big work was getting rid of, showing that 14 was impossible. And how do they show that 14 is impossible? Is they use computer search again. It's the only way we know how to do it. So what I mean is you find that there's a big enough finite piece that when you go and try to use the numbers 1 through 14 according to these rules, it's not possible. And that shows that 15 is. Now, the calculation took a while, several years of computer time. And we run into the problem, and it used a nice idea. So I just tried brute force search, storing this in an array. But there's things, some of you have heard of SAT solvers and things like that. There's ways that you can take the thing and make it into a logic satisfiability situation and use much more better tools that out there. But then it still took running time. It still took ideas to encode this in a nice way that would enable non-repetition. Took many years of computer time. And now we run into the problem, do we believe that? Because I don't think they ran the computer program, they just claim they did. They went off to the beach for 2 years and came back. So mathematics and computer science has a solution for this. So there's a solution for this, and this is called self-proving theorems. And that's not the right idea. But the idea is that you can take your huge computer calculation that you want to convince somebody else that that huge computer calculation is correct. And you organize it in a way, in the following way. So you take your thing and you produce a document which is a proof of your calculation. And understanding people do not have 2 years of free computer time just to go and do it themselves, let alone check that the programming is correct. So there's an idea is that what you can do is you can take, if you, the prover, trying to convince other people, you can embed it in this massive document with the following property, that if there's an inconsistency in that document, there's an inconsistency almost everywhere. Okay, so that I actually have seen I was a theoretical computer science student, so I actually have seen that. The idea, the analogy that would work is if somebody walks in and says, you said you have this consultant that you pay a lot of money and they have to produce a parabola for you, and they come back, and it's the wrong parabola. The real parabola and the wrong parabola are wrong almost everywhere. They might be lucky, they overlap in what, 2 points if you're lucky, maybe. That's the max you can do. So this is the idea, is that this is a theoretical, this is a known idea. So when I was a graduate student when this was happening, but in the early 90s, that they came up with the idea that you could take your proof, you could write it in a special language of logic, we're using zeros and ones. The other idea that is once you had a formula involving zeros and ones, it's also a formula for the integers. Crypto and other people know all about these types of things, extending from zeros and one. And then you had a situation, and I don't remember the details, I never even understood them when I was a graduate student. But nevertheless, you come up with this thing, and the way the game then plays is the person who's trying to convince you that this is a proof set. Here's the proof. You can't check the whole thing, but you can pick a point and say, convince me of this detail. And there's a protocol for doing that, that the proof they give you is going to be the same idea, but it's going to be slightly half the size. And then you pick a detail over here and convince me that is the. And the point is that, as I said, if there's no inconsistency anywhere in this document, there's an inconsistency almost everywhere. So if you pick something at random, almost surely you pick something that's inconsistent.
Is there a technical definition for almost everywhere in this context?
I'm sure there is a definition. So, I mean, say this is from the 90s already. I mean, there's a well-established idea of Arthur Merlin type situation. So Merlin is trying to convince Arthur, who's computationally challenged, of something being true. And there's a setup. All right. So anyway, so this is the thing, but the reason why why the problem ended up, what basically ended up in Esquire eventually, was that the final proof of this massive document with all the thing was, I think, something like 75 terabyte. So it's a reasonable thing. I meant to check. I believe somebody had made. I vaguely remember somebody saying this is now. Look at his books of records. It's the largest known to humanity. Anyway, so the student does all of this, very proud of it, and he should be. And I say nice. And then around about this time last year, one of the writers for the magazine Quanta, which is a mathematics and theoretical computer science magazine, comes along and says, okay, we're doing an article on this proof, but I get interviewed for this, and a few quotes of me appear in the paper, and my name is in print. And so I happily pass this fact on to my co-authors, and then a few months later, one co-author points out, hey, we just made it to Esquire magazine. and we don't get a shout out, but. I meant to show at least the quanta. The quanta actually had as a nice, an animation of that. I mean, rather than just giving the picture that they. I don't know how to. So the idea is they just show the numbers being increasingly taller in different colors, and that's the original batch. So that's not the contribution that they made. They were just showing that you couldn't do it with 1 through 14. Questions? Yeah.
So this pattern with 15 is periodic?
Yes. The student did say that they had done some sort of testing and that there are some slight variations on the problem where periodic doesn't give you the best number. But not for the original problem.
Is there something? Are there variants on the solution with 15?
Well, I mean, the answer is yes, but I don't want to create, I'm not trying to beat 75 terabytes. So what do? I do know that pretty soon after we did it, I mean, there's other grids. So there's a hexagonal lattice and a triangular lattice, and some people did those, and those turned out to be much simpler. So sort of, I think for one of them at least, you write it down, you draw the obvious coloring, and it's best possible immediately. Just the greedy algorithm is just one, and the other one might have taken a bit of work. But yeah, I mean, it's still not clear to me, though I'm the author of the problem, why it should be that the distance between 1 and 1 should be 2, and it doesn't mean 2 and 2 should be 3, apart from the fact we thought it might be interesting and seemed to have been proved right. All right. So my title has other problems in it, and I have 2 listed up there on the grounds that I thought 1, 2, I have 3 listed there on the grounds that I thought 2 wouldn't be enough and 3 would be too much. So let me pick. I'm only going to pick one of them and talk about it, and that is a much shorter proof. So there are similar ideas. So I'll leave the chessboard problems as a very nice thing for a talk in itself, and lots of things to be done there. I haven't actually ever done this. So this. So another problem that I worked when I was actually a postdoc was looking at this idea of mispackings of polyominoes. And I need to define a few things. So let me start with dominoes. So there's an E there, whatever. All right. The idea is you've got a checkerboard. This is very common again. Had a grid already. And you need to place dominoes on the checkerboard. So each domino covers 2 squares. But I'm not interested in what happens when you cover every square with a domino. That's a very interesting problem, and I think we had to talk about counting these matchings and other things in Math Club last year. So I'm interested in the reverse situation. What happens when you have as few possible dominoes on the board as possible? Okay, the answer is 0. Okay. As few dominoes on the board as possible, subject to the constraint that there's no room for another domino. So it's sort of like the minimum size of a maximal pack. So what you can't have is, I mean, what this means is I can go in here and that you've got a domino over here, and we're going to call this a hole. Oh, sounds very reasonable to call that a hole. So what must happen is you can't have two holes next to each other because they would have room for a domino. But you want as many holes as possible. You've got 5 on this. And the question is, what's the smallest best you can do, etc., etc. And this isn't the best you can do. Let me get myself. This is probably pretty good. Just let me raise and restart. Spike left. No. Raise, restart. I want a 6 by 6. And what I'm going to do is I can do a domino over here, which does 2 things. I leave a hole. I do a domino which does 2 things. I leave a hole. I do a domino which covers 2 things. I leave a hole, and so on that row. And then on the next row, I take the same pattern, but shift it over 1. We've seen this idea before already. Take this idea, shift it over 1. And so on. And if you think about this for a moment, what you get this particular thing, the number of dominoes is the same as the number of holes. So it goes domino, hole, domino, hole, domino, hole. Some of your mathematicians would point out that's what I just said is mathematical nonsense, because both dominoes and holes are infinite. And therefore both infinite things are always equal, and countable things are always equal. So what I mean is, if you could make this into a proportion argument, or you could make this onto a finite grid and then take the side and it goes to infinity, and or that compactness theorem, if you really want to do this mathematically rigorously. Or in other words, the holes cover 1/3 of the squares, or the dominoes cover 2/3 of the squares. That's mathematically defendable. So I said, look, there's a proof of this, and the proof is let's lead. And it's the following idea. What you do is you count the number of pairs the old combinatorics idea is you do this, you count the following. The number of pairs are where you've got a domino next to a hole. So for example, this pair would count 1, and this pair would count 1, and this pair would count 1, and this pair would count 1. They're right next to each other. The domino is touching the hole is touching the domino. All right. We're almost there. The claim is A is at most 4 times the number of holes, because every hole's got a domino around it. I think, in fact, on the infinite grid, this is equality. This is in fact equality. If you take a domino, there can be a hole here, there can be a hole here. These 2 can't both be holes. So only one of them is, so only one of them. corollary, number of dominoes. I'm sure there are other ways to do this, but that at least tells you that the number of dominoes must be at least the number of holes, and on any, okay, if you play this game on a finite board, you have to deal with dominoes on the edge and holes on the edge. And you can make all of that work, and it turns out when you do the adjustments manage to cancel not very nicely, so that if this, and then you can always get something provided the side length is a multiple of 3. If you've got a square with the side length is a multiple of 3, you don't need to actually don't need to do, you can do sort of alternate, maybe it's even length, I mean, whatever. There are some finite grids where you can get exactly D equals whole and asymptotically, that's the best you can do. So that wasn't me. That's known, that's an old problem. It was called the gun port problem. Things are times that people think about it. So I guess the gun port problem meant you were building bricks in your castle and you wanted to be able to have as many snipers there as possible, but not have the snipers themselves be vulnerable, I think was. Yes. Maybe we about ready for some update and some terminology. So what did I do? Well, I asked the question, what happens if you replace a domino by some other shape? So you've got a polyomino is a shape obtained like we have in Tetris, that you've taken some number of squares of the board and you created a shape out of that. So Tetris has got things like that and things like that and things like that. And you can then play the same game. How many ways, the possibly is not what you want to do in Tetris, is how badly can you do in Tetris, maybe. Except there you're doing it from the top. So, but assuming you weren't doing it from the top and you had to put things there and you wanted the game to finish as quickly as possible because you hated Tetris. And so let me just show some pictures. Why don't I have the right thing? Okay. I need to add it up. Yeah, I probably should keep the story thing. So one of the nice things at graduate school was Kleitman is a combinatorialist, and his teaching assignment was to run a seminar, which meant he sat at the back of the room when we gave presentations, much like I'm doing here. And somebody gave a talk about, I think maybe the original thing, and this motivated me to actually to do the. So I have results. I'm going to spare you the algebraic formulas and things. But for example, you can take the tromino now, the thing on 3 things, and you can ask, how does it fit? What is the best tiling? And it turns out this is the way to put it. So you can have lots of holes next to each other now, but there's still no room for one of these to fit into this particular diagram. And if you do squares, that was particularly uninspiring, but nevertheless, you can at least ask, you want to do a 3 by 3 square, such that you don't have any room for another 3 by 3 square. It is what you expect. Put a 3 by 3, then leave a gap of 2, then put a 3 by 3 and leave a gap of 2. And obviously, this is not the only way you can do it. You can take this picture and share it and do various things. And the techniques are somewhat similar to the number things that I think. And then I leave left the following as an unsolved. So if you take the dominoes and just take the straight domino, and I could prove it. But if you go to the 1x4 or the 1x5, I wasn't able to show that this is the best possible. So when I haven't kept up with this thing, but certainly a lot, maybe 5 years ago, I did check and it was still unsolved. As to show that in general, if you're trying to cover the checkerboard with these 1x n pieces, subject to the constraint that there's no room for any more 1x n, where you're not allowed to rotate. I should have made that at some stage. That's the best possible. Questions? I got a minute for my Tetris story. So Tetris was a great student again. I'm useless at these things. I spent hours trying to get reasonably good at Tetris. And one glorious day in May, I managed to have a really good run, not like it was on the news recently about somebody reaching level whatever. And I made it into the top 100 list of people at graduate school. And on the Monday next, they reset the list for next year. And I do not like Tetris ever again. All right, thanks for coming.
Questions?
Yeah,
Has this generalized at all to where you start allowing multiple shapes and you're still trying to leave as many holes, or are you just using a uniform shape every time?
I think people have tried multiple shapes. Yeah, I'm pretty sure there are results about multiple shapes, but I haven't kept up with the literature, so. It's just, here's another checkerboard.
Other questions?
Yeah, at the back.
So can you show me the board, the hidden part of the board?
Sorry?
I want to see the
Where's the
board.
screen?
Yeah, now screen is blocking the board, but there was a question.
Oh, okay. You wanted the board, the checkerboard, that's.
Oh, you erased it. So there was a question 3, right?
Sorry?
There was a question number 3, but you erased it, right?
Yeah, question number 3 was the one that was the number where the answer was 15.
It was any 2 copies of I are more than I apart.
Yeah.
And I have a question about question number 1 and 2. So the question 1 is the case when second I was 1, right?
Yeah,
And the question number 2 was the case when the second I was 2, right?
yes,
And when second I was 0, the answer was 1, right?
yes,
When second I was 1, the answer was 2.
sure,
And when second I was 2, the answer was 5.
yes.
So I just wonder, for a fixed value of k, when the second I is k, is there a formula?
I'm pretty sure there's a formula.
I'm asking this because 1 to 5, those are Catalan numbers.
Sure, I mean, well, there'll be the size of the square of the circle and that norm around the vertex. So, I mean, when you have distance, I mean, they'll be at least related to that thing. I mean, and I'm pretty darn sure you can pack them perfectly without any wastage, and then you can shift the picture over without, once you can do that, then you can.
I'm assuming you had to figure that out exactly to show that that sum was greater than 1. You had to determine that sequence.
We don't have to do that. I mean, all of that, I think once we got to the sum was bigger than 1, it didn't look like a fruitful avenue. It's clear, I mean, in the original thing, that the best strategy for 1 and the best strategy for 2 can't be simultaneously achieved. Because when you think of the checkerboard, all the ones will be on the white squares, and if you do the best strategy for 2, half will be on the white and half will be on the black. So we briefly tried to put a theorem about what's the joint best you could do using 1 and 2, but it didn't look like it was getting us anything. No, if the answer was going to be finite, it was a good. If the answer was going to be infinite, arguing about whether you use infinity or finity plus 1 wasn't going to get us anywhere.
Other questions?
Let's thank our speaker.
Oh, thank you.
Thanks for coming.
Just now that I didn't think it was one, but you.
Everybody have a good weekend. We will see you next week for